Today we are going to measure the wavelength of 3 different laser diodes using diffraction gratings and Young's double slits. First thing I'm going to do is look up what I think they ought to be. We're going to be using a red, a green and a violet laser. So cheap laser diode wavelengths, just Wikipedia will do. Laser pointer, yeah, it's one of those cheap laser pointers. If I scroll down here, there's a table of wavelengths. So I could reference that, or I could click on here and dig into one of these. Don't even know if I can get to it. Somewhere in here it might even tell me. So I can follow the references on Wikipedia to find what they are. But this is A-level. I can probably just get away with referencing that. It's fine. As long as I date when I've accessed it, that'll be fine. So I've recorded it in my lab book. That is what I'm hoping to get from this experiment. So the equipment I'm going to be using, I have these very cheap Chinese lasers, which, there we go, that's a red one. Simple push button to operate. I've got a few of these. The reason I've got a few of these, yes, they're different colours. So this one is some sort of red colour. This one is green. And this one is blue. Well, I think it's actually violet. Certainly that's how it comes through on the camera. And if you look on the violet one, don't know if you can see that, it says, it's out of focus, 405 nanometers. At least that's what my eyesight says that says, which is what it said on my reference. I won't trust what it says. I looked up what it should be. This green one here, this one says 532 nanometers. Hopefully you can see that. And then we've got this one. Now this is an interesting one because this laser is a red coloured laser, and yet on the red laser it says 532 nanometers. Interesting. I don't think I trust that one. I don't think that is 532 nanometers. I just looked it up. 532 nanometers is a green laser. And yet this one has a little red arrow and produces a red dot. So that is the problem with buying cheap Chinese lasers. But here's one that claims to be red, looks red, and on the label it says 600 and, let's get it in focus, 650 nanometers. Or thereabouts. So, we've got 3 lasers. One of them as well is the same as the others, except it says the wrong label on it. Won't bother using that. What else have I got? I've got some diffraction gratings. I've looked down here. I've got 300, 600 and 1,200 lines per millimetre diffraction gratings. Fine. I've got some double slits. I've got 100 micrometers separation, that's 0.1 millimetre separation. I've got 0.5 millimetre separation, or 500 microns, and I've got 1,000 micron separation, or 1 millimetre separation. Those are the 3 sets of double slits I've got. And with all of this, we're going to see which apparatus we can use, which we can't. We probably can't use all of these. We have to decide what our variables are, of course, but let's do some preliminary measurements to see actually what will work. I would like to measure the wavelength of all 3 of these, so I'd like that wavelength to be the independent variables. In terms of graph plotting and things, you probably don't actually need to plot any graphs for this, but it might be a good idea to do so, so that we have some repeat measurements. I've got this, which we could use to hold the slides in place. That does have drawbacks. I've got this as well, which has its own drawbacks. The drawback for this one is it's not going to hold the slide perfectly vertical. I'll show you what that does in a moment. This has the same problem, but this can be easily solved with some physics putty, shoving it in the edges to try to make this as vertical as possible. Hey, it's an A-level practical, it'll be good enough. I've got vernier caliper. The vernier caliper might be useful for measuring small distances, but I do have to be careful because it is shiny, and therefore if I have a laser and it's pointing at my vernier caliper, it is possible that I could get a stray reflection straight in the eye. Can't do it when I try to, but oh, there we are. Oh, straight in the eye. So we've got to be careful when using shiny stuff. Don't stick this in the path of the laser beam. Got some paper and some masking tape, which I can use to stick a screen up on the wall over there. Meter ruler to measure the distance between the slits or the gratings and the wall where the screen will be. And to trigger the laser, we're going to use this claw here. So if I just take the red laser to start from, I could pop it in and then just tighten this very, very gently so it just holds it in place. And right now the laser isn't turned on or anything. But if I turn it a little bit more, it just pushes that switch and turns the laser on. So you can have the laser off and then laser comes on. And that's good enough. Don't tighten this too much or you're going to crush your laser and damage the switch. So let's just loosen this. You can see it's turned off. Tighten it just a tiny bit. There we go. Now the laser's on again. And that's all we need to use for that. Now the issue with using this particular slide holder with the crocodile clip, not the fact the crocodile clip is shiny or anything, so it's not holding it vertical. So if it tilts it this way a bit, can you see the way the dots on the wall curve from the center being highest, and then the second, third, fourth order, they curve downwards. And if it tilts the other way, they curve upwards. So we can easily check when we're vertical enough by adjusting this until it's pretty much vertical. We can actually use some sort of straight edge to check when that's slide is vertical, but again, it's A-level practical. It doesn't really matter if it's perfect. So we could use this. We could also use our wooden box like this. Of course, I have to adjust the position of the laser. This slide doesn't actually fit in the wooden box, and yet this one does. That's interesting. So let's just turn the laser off and move it out the way. Some of these slides do fit in these little grooved wooden boxes. Some of them I've just discovered this very moment. It's 300 lines per millimeter diffraction grating. It doesn't actually fit. So it looks like I'm going to be stuck using this thing. It's okay. We can make it work. Where the wall is, I've got this rather irritating lip there. So if I put the ruler against there, it's not against the wall, which is where the screen will be. So I make that 1.7 millimeters. I'm looking at it directly onto the scale, 1.7 millimeters. So I need to make sure the slides are 1.7 millimeters from the other end, so I know they're a meter away from the wall. That could be quite difficult to determine because of the thickness of the slide and trying to line it up. But again, A-level practical. Let's just add a centimetre of uncertainty to my measurement of that distance. Let's say it's 1.00 plus or minus 1.00 plus or minus 0.01 meters. The distance between the slides and the screen. And that's good enough. I'm not measuring the distance between the slide and the screen to the nearest millimeter because of how much uncertainty there is in this and the fact that I've had to move the ruler from the edge here down to there. I just think that's not sensible to try to measure a number to the nearest millimeter. So what are our two experiments? Well, we're going to be looking at n lambda equals d sine theta, and I want to have it so that I do this 3 times with 3 different wavelengths, so I can get the wavelengths of each of the lasers. So you could say the wavelength is the independent variable. Well, what would the dependent variable be then? Well, diffraction angle, I guess, would be sensible if you measure to the same order each time with the same number of lines per millimeter on the diffraction grating. That would work. But then, of course, we want to calculate the wavelength from some sort of graph. So we want that to be the gradient of some sort of graph. So perhaps we could do a graph with 3 points for the 3 different diffraction gratings that we've got. That's a possibility. So preliminary check to see whether that's actually sensible. This slide is roughly in the right place. And yeah, I can measure the distance between those orders. And if I know it's a meter away, I can determine the angle of diffraction. So where's the first order? Let's get out a second laser pen. Let's get out a red one so I can point to the 0th order. The 0th order is that one there. So that's the first order there. That's the second order. So if I measure to the first order, then when I get out the 1,200 lines per millimeter slide, like that, the first order is, oh my goodness me, it's gone off the screen as you can see it, probably. It's all the way over there on the right somewhere. I'm just going to have to move the camera back a bit so you can see where it is. So the first order, is it on the screen yet? It's all the way over there. Can you see it on the right? There's the first order. Let's just tilt that. All the way over there on the right. Over there, probably behind, oh no, it's not behind the metal post. There it is. So that's the first order. So if we're going to do this, we really can only measure the first order for each of the diffraction gratings. That's all we can sensibly measure. So let's do that. Let's say use the first order and measure for the 3 different d values what the 3 different thetas are. That's a diffraction angle. Of course, I'll have to measure that. And produce graphs to get that. So if we rearrange this equation, we'll have sine theta is equal to 1 over d, or say n over d. N is going to equal 1 anyway, multiplied by lambda, like that. If I plot that on the y-axis, that on the x-axis, that will be the gradient. Great. 1 over d, well that's handy, because with these diffraction gratings, I'm given what 1 over d is. 300 lines per millimeter, which is the same as 300,000 lines per meter, and that's 1 over d. Well, d is the distance between each line, so that would be, for this particular diffraction grating, this would be 1 over d is 300,000. So that makes it actually a little bit easier. I don't have to take reciprocals of 300, 600, and 1200. Oh, nice rainbow pattern on the paper. Anyway, I don't have to do that, so I could just plot my 300,000, 600,000, 1,200,000, n is equal to 1, and I can just plot that straight onto the x-axis. And the y-axis will be the sine of theta. How will I calculate theta? Well, I'm going to have my 0th order here. This distance is 1 meter. I'm going to have my screen like this. So the first order is going to be there. There is my theta. And I can measure this distance there. Let's just call it x. And so what's theta going to be? Well, theta is going to be the arctan of the opposite over, well, if I do everything in meters, that's just 1 meter. So it's just 1. So it's going to be the arctan of x, which is going to make it easier if I use meters. And so it's going to be the sine of the arctan of blah, 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 blah. That works. So I'm going to end up with 3 tables for the first part of this experiment. 1 over d, because n is going to equal 1. 1 over d measured in meters. The x from that diagram measured in meters. Theta calculated using this. Sine theta. And then I will plot sine theta versus 1 over d. And that will give me, the gradient of that will be the wavelength of that particular laser. So what about the second experiment? In the second experiment, I'm using these things. And so I want to do a quick preliminary check to see if when the screen is a meter away from the slits, can I see the diffraction pattern? So let's just see if that's the case. Let's pop my, there we go, the closest slits together there. Let's just use red and trying to line it up whilst looking at the camera screen is tricky. Can you see that on the wall? I reckon I can make that out. Let's move it closer. Yeah, on the wall it looks like that. And I reckon you can make out the distance between those fringes. Let's do it for the 0.5 millimeter separation. Oh, no, I don't think that's going to be any good. Try the green one. No, definitely not. I don't think that's going to be any good. Let me show you what it looks like up close. You see now the problem is that we've got these fringes in here. We could possibly make out 3 fringes there. But then we've got the dark fringes from single slit interference superpositioning with the light fringes that would be there from the double slit interference and making the spacing look wider than it is. Possibly use this with the 3 right in the middle. Possibly. Let's just try the other one. So these are 1 millimeter slits, separations, and now I don't know if this pattern I'm seeing here is from single slit diffraction or double slit diffraction, so I can't use this. So at most I can use 2 different sets of slides, probably only use one of them, and so there really is no point thinking I'm going to switch out the slit separation as my independent variable. That's not going to work. So we can only use that slide really to get sensible results. What's the equation? Let me derive it very quickly. Give me a second. I always have to derive this equation in my head because I can never remember it. Right, there we go. That's the equation for diffraction gratings. I might have written it a bit too small there. We're after lambda. We can't really change S, the slit separation. That's going to have to be a control variable, or we can't make any sensible measurements. Which means that all we can do is change D and measure W to determine lambda. It's a little bit of a weak practical, but okay, so let's rearrange it. We could say that W gets plotted on the y-axis, and we could say that D over S gets plotted on the x-axis, and the gradient would be lambda, just like that. That would work. We could change the position of the slit relative to the screen using the ruler we've got, so we could have different values of the big D. S is going to be fixed. S has to be this one. We haven't got a choice. And W, well, we can mark off on the screen where the fringes are and how many fringes, and then use vernier calipers to try to improve the resolution of the measurement that we take. Well, the resolution of the instrument, so it improves the precision of the measurement we take. Improve the accuracy of the measurement we take, I suppose that's correct. But we'll see what happens. But we do want to do it for all 3 different lasers. So we're going to have 3 tables for this one as well. But there'll be much less processing for this one because you're just going to measure those numbers. Right, okay, I've thought about it, I've done some preliminary measurements, it's taken us 20 minutes, but we're ready to start the practical. And you know, that is such an important first step on this practical, is figuring out what you're doing. Right, let's put a subtitle. I would say always draw your tables in advance. Having said that, always leave a bit of space in case you need to take more results. As it is, I'm not going to bother with repeats because I'm doing them already. So you know, with how many times I'm doing this experiment. So I think that'll be fine, and I'm not leaving extra space in case I need it. I should probably draw a quick sketch of the diagram so that I know what these different values mean. 0th order, 1st order, and I can label that theta, and that 1 meter. It's just what I'd sketched on that piece of paper. Now, I have the privilege at the moment of being in a lab by myself, and so the safety concerns with the laser are only affecting me. Okay, I've only got to be worried about myself and the laser and making sure I don't accidentally illuminate my eyes, because that could be damaging to them. If I'm doing this in a lab with lots of other people, well, I've got to be careful then, and I might use some sort of shielding around my laser, some sort of box, cardboard barrier. It doesn't really matter. It's just anything to stop those spurious reflections, because you will get reflections coming back from these things. They're shiny glass, and you've got to watch out for those. Also, you're going to get diffraction orders going off all the way around to 90 degrees, so you want to make sure that no one is crouching down, putting their eye in the horizontal level where the laser beams are, forward from where the slits are. So what's our first one we're going to do? Let's do 300 lines per millimeter. So let's do 300 times... now, which way was I doing this? It was 300 lines per millimeter. I want it in lines per meter. So that's going to be 300 times 10 to the 3 lines per meter. Then we're going to have 600 times 10 to the 3. I should have put the times 10 to the 3 up here, shouldn't I? What a wally. And 1200 times 10 to the 3. Now, I wouldn't usually write these numbers in advance because you'd actually have to measure them, but I don't really have a nice easy way of measuring these. I just have to kind of trust what it says. So 300, 600, 1200, I might as well write them in advance. Let's say I've measured them because I read the number. Might as well fill it in for the others as well. So let's get all this set up so you can see what I'm doing. It was, just double check that again, 1.7 centimeters from there. Let's get the 600 lines per millimeter. I might as well do the 3 colors. It's easier to move the color than a slit, the color laser than a slit. I'm just judging by eye that it is 1.7 because these are all going to be plus or minus a centimeter. I'll have to record that somewhere. I mustn't move that. So now let's turn on our red laser and measure the distance to the first order. And as I'm not moving the 300, I can go ahead and just take the ruler. I'm going to draw on a screen. And this is going to be, to the nearest millimeter, 20.0. Write that in the book. Red 320.0 centimeters, but I'm doing it in meters, so 0.200. Let's change out the laser color. Let's move the camera down so you can see better. So I'm leaving the, let's do green next. Where's green? There it is. I'm leaving the slides in place, the slits in place. I'm not touching them. There we go. Measure that distance. There's the 0th order. Line it up. 16.2 centimeters. So that's 0.162. Just realised I've written it in the wrong place on my book. But that's okay, I've corrected it. And then switch it out for the violet one, which I often call the blue one. I think it's more blue than violet, but there we go. Measure that distance. 12.3. 12.3, so 0.123. Okay, now change out this for the 600 lines per millimeter. Look how quickly you can do this. position it. It was 1.7 away from the wall, which is there. Let's go with the red laser first. Pop it in, switch it on, get it lined up. Measure the distance to that order. My arm's getting in the way. 44, pretty much exactly 44. And what I could do is measure it for this order and that order and take an average, but I'm not going to do that because I can't be bothered. So 0.440. It's extra time. I've got enough data coming in anyway, so I don't think there's really any advantage to me doing it. Not when all the distances are to the nearest centimetre. What is the point? There's going to be some significant uncertainties on this. So that is lined up there. 35.5. So 0.355, 35.5. Switch it out for the violet one. I'm doing this in quite a bright room because, well, I can. It doesn't need a dark room, really. 25.9. So it's lined up there. Yeah, 25.9. So that's 25.9, 0.259. And then switch out for the 1200. I'm not even going to pause the video. I'm just going to keep doing it because you can see how quick this is. Let's just pop that there. Pop that on 1.7. This is about there. To near a centimetre. Take out my red laser. Pop it in its holder. Oops. Line it up like that. Should be. I mean, I haven't done anything to make sure that this laser beam is perpendicular to the wall, and it really should be. Oh, crikey. Look how far away that order there is. This is definitely not perpendicular, because as I move it around there, it makes real changes, but never mind. That's more than a metre. So I'm going to use my handy masking tape, and I'm going to have to add some uncertainty onto this. What I'm going to do is just using my trousers, just take off some of the sticky from the masking tape so it doesn't damage the wall. And I'm going to pop that there. I'm going to go this way, because it should be symmetrical, it shouldn't matter. I'm going to go this way, and I'm going to put a bit of masking tape and mark off where 1 metre is. So I'm going to have to double whatever this uncertainty is. And then that's 1.207. 1.207. 1.207. Oh, this is the 1.207. This is red with 1200. What on earth is green with 1200 going to look like then? Have I messed up? Let's get the green out. Am I even going to be able to see the green? Should be able to. Yeah, I can measure that one directly. Right, okay, let's do... I haven't moved the slits, so let's do the green one next. I've messed up, I wrote it in the wrong place on my damn table again. Should make sure the laser beam is perpendicular. It's close enough, I'll just do it by eye. Line it up there, don't turn around, because you'll blind yourself. 77.6. 0.776. And lastly, the violet one. Pop that in there. This is the last result for diffraction gratings. That's how long it takes. Yes, you could take more care. Yes, you could do a better job. These results will be fine. Line it up. 53.4. 53.4. and you'll see where I messed up on the table. So on the table, I wrote the red one where the violet one should be. Never mind, I crossed it out. With the red one, I am going to make a little note just next to it that this is 2 times the absolute uncertainty in x. And I should probably record what the absolute uncertainty in x is. So I can have to do, I'll fit this in the bottom, it doesn't really matter. I'm going to say that the absolute uncertainty in x is probably a millimetre times 2, so probably only 2 millimetres, but let's say 4 millimetres to be safe, because the dot did have some width to it, the order. I can say that the absolute uncertainty in the distance to the screen, let's call that big D, that's going to be 1 centimetre, where big D is equal to 1.00 meters. I've changed it to a big D there. So I can use that to calculate theta, and I can do the uncertainties in theta later. D, I've got them recorded, and I have no information about the uncertainty in them, so let's discard the uncertainty in them. Right, that's all the data I need for this practical. So the next half of it, which takes much less time, is this bit. So we decided that we were going to use these slits with a spacing of 0.1 millimeters. They record that as S. And this was the equation that we were going to investigate, where we'd have 3 different sets of data for 3 different wavelengths of lasers. We're just doing the experiment 3 times. Independent variable will be D, that's the distance between the screen and the slit. W will be the fringe spacing, which I'll have to measure. So here are my table of results for the red, the green, and the blue. It's not calling it blue, are we? The violet lasers. There we go. Mistakes are allowed. Some people get all fussy and say you should draw the box around the tables. I'm not that bothered about it. If I want to add that later, I can, but that should be fine. There's going to be some uncertainty in D, which I can record down here on the right-hand side somewhere later. I'll have to make a judgment about that during the practical. N is going to be how many fringes in that central bright fringe I can see. In other words, how many of the double slit fringes can I clearly see? NW, that's going to be the width of those N fringes, and I can use that to calculate W. And then I will plot D over S on the x-axis, W on the y-axis, and lambda with the gradient. So there are my tables laid out. I reckon I can do 1, 2, 3, 4, 5, 6, 7 data points for each of these. Bad planning, I ran out of space at the bottom, so I'm going to end up writing on the margin there, which isn't great, but it should just about fit. So let's get it set up again. Now what I'm going to do is stick a screen to the wall. But to do that, I want to make sure that the masking tape doesn't pull the paint off. So I'm just going to get rid of the sticky from this by using my trousers. You probably hear it there, sticking to my trousers, peeling it off a few times, trying to pick up a little bit of fluff so it doesn't stick quite as well. That's the plan. And then we're going to pop that on there, and just a bit of tape across there just to hold it in place. And let's do the red first. So let's label this so I don't forget. Red. Okay, let's get the rest of this set up. So this is how it looks without a screen. I could probably push the laser a bit closer, but it doesn't really matter. So we've got the laser, switch held on by the clamp, gratings, it's not a grating, it is 2 slits. I'm taking no steps to make sure that that is perpendicular to the wall, I'm just doing it by eye. I'm going to position it while looking above. Bear in mind it's going to be about 17 millimeters. About 17 millimeters further away than it should be. So I have to subtract 17 millimeters from each of these measurements. And that's what it kind of looks like there. So I'm going to have to be quite careful when I draw from the centre of the spots. Right, okay. So my first data point is for 1 metre. I reckon I can see the centre of that spot. 1, 2, 3, 4, 5, 6, 7, 8. The centre of that spot with the naked eye. And I can label that 1, 2, 3, 4, 5, 6, 7, 8. I can label that n equals 8. D equals 1.00. There it is. And now what I can do is actually move the experiment to somewhere slightly different and do the next one and then the next one. And I can analyse this later. You see, I've moved it and you can see the centres are no longer lined up. So let's go with 95 centimetres. So that's 95. It's actually easier just to move the paper. Let's move the paper over to there and do that bit for 95. Push it flat against the wall. Right, so where can I see? I can see the middle of that one very clearly. Oops, slightly to the left. 1, 2, 3, 4, 5, 6, 7, 8. Probably to the middle of that one. So 1, 2, 3, 4, 5, 6, 7, 8. Not sure I can get to that one. N equals 8 again. And this is D is equal to 0.95. And we're going to keep on doing that, moving the paper each time, 2 notches, 2 notches. What I could do as well, whenever I move the paper, I could draw a line connecting those 2 notches so I know that they're connected with each other, so I know what's going on. Let's keep going. Right, there we go. So that is the full set of results taken. I can switch the laser off and have it on longer than is necessary. Let's have a look at these results. You can see I worked my way around the page in some random order, but now I can get out my vernier calipers, measure, 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 and enter them on my table. Now there's a good chance this will end up being no more accurate than just using a ruler, but let's do it anyway. Line up that with the very beginning, line up that with the very end, in so much as I can, and read off that vernier scale. Possibly see that there. It's not an easy scale to read, you see. But I make that 5.1 to 5.26, 5.27. Let's call it 5.27. 5.2. And I reckon it's on the 7th one or the 6th, or maybe the 6th one. No, let's go 5.27. So I reckon that's 5.27. So here we go, it's with red. This was for 1.00 metres. N was 8, and that was 5.12. I've forgotten already. 5.27, I think it was, wasn't it? Let's read it again. So I should write things down. 1, 2, 7, 5.27. Or 52.7 because I'm using millimetres. I must make sure I'm careful with these units later, especially when I'm analysing the results. So that divided by that I'll write in there, but I can do that at the end. So I'm going to do that with all of these. The next one was 95, 0.95. Let's move this so you can see. That's the next one. That was also N equals 8. Not 8 lines, 8 gaps between lines. The vernier caliper comes out. Place it right on there, as close as I can, and right on there. And then the pen thickness is about 1 millimetre, so this is overkill and probably absolutely unnecessary. Because of the pen thickness. I mean, how thick is that pen mark is going to be? I could get a travelling microscope out and measure it. This is just absolutely pointless doing this. I might as well use a ruler. 5.11. I make that 5.11. You possibly can't see it very well. It's gone past 5.1, and I reckon, you get it just the right angle, I reckon that's 5.11. Not easy to see. 51.1. So I'm going to do that for all of these. I'm going to stick with using this because I've started. Regret it slightly, but that's what I'm going to do. Last one. $31.2. So they don't take long to do when you get into the throw of it. Yes, I read 45.1 and started writing 54.1. Caught myself. Mistakes do happen. Right, before I do any analysis, I might as well do the green and then the violet. And it's exactly the same method as I've already done. So I won't record that. I'm doing the same thing. And unless something interesting comes up, I'm not going to bother recording it. So there's the one for green. Did it all. Already measured it all. Stuck it in the table. Now for the violet. Thought you might want to see how quickly I can do it now that I'm in the practice of doing it. I've done the 1 meter, the 95 centimeters, the 90 centimeters. So now I'm going to line up 85, subtract that extra bit, the 17 millimeters, position the laser there so that I'm happy that everything is straight. I can barely see this. When I put the paper there, I'm not even bothering to stick it. That makes it much easier for me to see, and I'm not turning around and facing this way, marking off 1, 2, 3, 4, 5, 6, 7. It seems to be, a bit further over, it seems to be 8 orders, not orders, 8 fringes, or 8 fringe spacings is all I can see no matter what I do. So that's 85. Let's do 80. Subtract the 17 millimeters. Let's move that to there. Make sure that that is square on there. You can barely see it by illuminating both slits. Make sure that's square. Make sure that that is square on there. That's better. See if I can see this one. This was 80. Yeah, I can just about see that. So that is there. 1, 2, 3, 4, 5, 6, 7, 8. That horrendous noise is the school bell to tell me that the lesson has ended and another lesson is about to start. But it's not in this room. But it might get noisy outside. So I've got 1, 2, 3, 4, 5 measurements there. I'll keep on going while the crowds disperse outside the corridors. So there are my violet things. I stopped taping it to the wall and just held it up against it to make it quicker. I had to turn the lights off because I couldn't see it. So there were some adaptations I had to make to the practical because I couldn't do it using the method that I was originally following. I mean, making the room dark was important. Anyway, I've measured them already using the vernier caliper. I've already chucked the numbers into the table and I have done the calculation. That column divided by that column is that column. I managed to get 8 fringes, or 8 fringe spacings, should I say, every single time. So there my data, and I'm going to plot that on the y-axis and that divided by that on the x-axis. So I need another column for d divided by s. And so there we are, I've added it, and I've made sure that I was using the same units here, because that really ought to be dimensionless and unitless. So I did d in millimeters divided by that in millimeters. Hang on, that's wrong, stand by. This is why we check things. Everything here was 3 orders of magnitude wrong. Silly sausage that I am. So glad I spotted that before I got any further. Yes, I made d in millimeters. So 1,000 divided by 0.1 is 10,000. And 0.95 divided by 0.1 is 9.5 thousand. As it should be. And I went down like this. Now, there's a word about significant figures. Because this number, which was given to me on the slits, is given to one significant figure. Which means that, really, because we're doing a calculation, these should be one significant figure. But I don't think that's a very sensible thing to do. These are 2 significant figures, that's 3, but let's go with the 2 significant figures. I decided the sensible way to round it would be like this. I mean, I'm plotting it on a graph anyway, but I thought that was sensible. And I've got some more data crunching to do from the diffraction grating before I can draw any graphs. Because I still got to calculate theta and sine theta using this equation to get theta and then sine of that equation. So let's get crunching. Just finishing off the last calculation. Sine of 7.01, 0.122. Sine of 14.5, 0.250. And sine of 28.1, 0.47. One. There we go. That's going to be on the y-axis. That is going to be on the x-axis because n was 1 each time, so that's just going to be what's on the x-axis. And the gradient ought to be the wavelength. Right, we've got our tables of data. I haven't even thought about uncertainties apart from some brief mentions here. So I should probably record something about that on here. Yeah, let's say that the absolute uncertainty in NW was equal to, I mean, it was a 1/10 of a millimetre, but let's say 2/10 of a millimetre. Just like that, in case that's useful later. And uncertainty in D here, like 4 millimetres, same as it was over here. Oh no, I used one centimetre there. Should we use 1 centimetre? Seems a bit much. Yeah, let's use the same absolute uncertainty as I did in that practical. It seems a bit much, but yeah, it doesn't matter. Big uncertainties just means big error bars. It doesn't mean the results are bad. So, right, let's think about graph plotting then. If I'm going to put this on the x-axis, it needs to go 12 wide, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9 squares. We could do a false origin. 3 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Hey, that will work. That will fit perfectly. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we are. So you can't see what I'm doing. Going 3, 6, 12 with a false origin. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that will fit perfectly across there. Now, y-axis, which is this one here, goes from as low as, I'm going to plot these on the same set of axes, as low as about just below 12 to as high as around about 77. 12 to 77. All right, so 77 minus 12. Oh, brain's turned off. 65. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 65 into 14. Let me pause the video while I think. Yeah, that didn't take long at all. I could actually just go up in 5. So if I go from here, 12, right from the corner, yeah, let's go up in 5s. I don't like going from 12 in 5s, that's the problem. Let's go from 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, and it needs to go up to 77. So my axes are right at the edge, but that's okay. Downside to the axes being right at the edge, I'm using some terrible ruler, is it makes the line too thick if the page moves, but I'm going to go with it. I'm sure it'll be fine. Let's do that one as well. Right, like that. Let's label them. So this isn't great. I should really have gone 300, 400, 500, 600 and actually labeled them and put the 10 to the 3 in there. And actually I wrote sine theta here because my brain has turned to mush. But I, wrote sine theta. No, that goes in the y-axis, crossed it out. Again, mistakes are allowed. It's a lab book. It's a working document. It's not a write-up. So 300, 600, 1200 with a 900 there. But those numbers are more than 5 centimeters apart. So that's not really acceptable. I should have put 400, 500, 600, 700, 800, 900 like that. So that's not really acceptable. Right, let's go on the y-axis, and they go up just like that in 5s, as I had said. 0.10, 0.15, 0.20, and so on. Let's plot the points. So they're the 3 points plotted for red, there, and all the way over there. Now you can see the value of a 30 centimetre clear plastic ruler, but I will add error bars to that because they're not perfectly along a line. So let's think about these error bars then. And I can't do much about that because I don't know what the uncertainty in that is. So I'm only going to have to look at vertical error bars. When we use the largest value of x, so that's going to be 0.200 plus 4 millimeters, and the smallest value of d, so that's going to be 1 meter, subtract 0.01 meters, that's going to give us the largest value of x over d, which gives us the largest theta, which we can do the sine of that theta and get the largest possible value of this data point. And that works out to be 0.202. And do the same thing with the smallest possible value of x. So that's x, subtract this absolute uncertainty. And do the same thing with the largest value of d. It's 1 meter plus that absolute uncertainty. That will give us the smallest value of x over d. Arctan of that, and then sine of that gives us the smallest value of this data point. And so you can see, although this is 0.196, which you can plot as well as we can, it could be that much or that much, so anywhere between that range. So when we draw our error bars, it actually works out to be just a small square up or down on the error bars. Not very much at all. So let's just check another one. I might do all of these and get a feel for it, but I'm not going to do that for every single one of these 9 data because I think that would just take a bit too long. And if they're all going to come out about the same, there's no point. This one's interesting because we said that there was double the uncertainty in the measurement of x because I had to use 2 rulers. So I take out this awful calculator and let's do the largest value of this data point. So it's 1.207 plus 2 lots of that, so that's 0.008. Remember, it's in meters. Now I have to put brackets in all this. So that's the largest value of x divided by the smallest value of, I hate these calculators, divided by the smallest value of d, which is our 1.00 subtract 0.01. And that is the largest value of our x over d. Now I take the arctan of, not option, I'll get back to what I had before, arctan of that. So 50.8 degrees is the largest angle, and take the sine of that, 0.775. Looking at it, that's a small square as well. So I'm just going to go with a small square vertically for every single error bar. I'm not going to bother calculating it for them all. It's not necessary. If I was using a spreadsheet, then it would be slightly easier to do that, and I probably would. But remember, these are just estimates. These are estimates of the uncertainties. So that's good enough. Right, I've got my 3 error bars there. Now I need to draw my line of best fit as best as I can. See if I can get it to pass through all of those. Oh, so close. Actually, I think we can just make that work. If it clips the top of that error bar at the last data point, the top of the error bar at the first data point, it just about clips the bottom of the error bar there. Oops, so that is our line of best fit. I'm pretty happy with that. Now I should label that red, and I can do gradient calculations for that later. But there they are. It just actually lies just outside this error bar, but it's pretty close. Right, now we're going to do the rest. So let's plot the rest of these points. And it looks like that. So the red one is there, The green one is there, and you can see that it's a little bit further outside these error bars. I might just double check what the error is on that one, the lower bound is of that one, just to see whether actually I should have made the error bars bigger. So I get my calculator out, I want the lower bounds, that's the smallest x, that's 0.335, let's put the brackets in, 0.335 subtract 0.004, then divide that by the largest value of d, 1.01, do the arctan of that, and then do the sine of that, and I get 0.311, 0.311, yeah, actually that error bar would cover that. Look, you can see that 0.311 is actually about there-ish. So that's within that uncertainty, really. So been a bit lazy with my error bars, and actually when you do include them, it looks like the line does go through that data point. Maybe I should have done the errors for all of them. But at A-level, we're not actually required to do them, so it takes a bit of time to do them. I'm not really inclined to do it for every single one. Now I want to. 335 plus 0.004. I'm going to go with the largest one, see. Divided by a smallest value of d, well, 1 subtract 0.01. Okay. Arctan of that and the sine of that, 32.4-ish, 31, 32. How have I got 33 there then? Have I done a mistake with my calculation for that data point? That's possible, because I've got 32.4 then. 31, 32.4 would put us about there-ish for the error bar. Just double check that calculation. 0.335 divided by 1. Don't know why I bothered doing that. Arctan of that, and then the sine of that. 31. Where did I get 33 from? How very odd. It's 31.8. 31.8. Look at that. I made a mistake. Let's cross that out and rewrite it. 0.318. Puts us about there-ish. Bang on the money where we wanted the data point to go. How about that? Oh, I'm going to spot check some of these others as well. Let's just do the middle one there as well. Make sure I haven't been a numpty with that one. So 0.534. Divided by 1 is fine. I don't have to do anything with that. So arctan, you have to do it the other way around in this calculator. Let's do that one, 259. 0.259, and then the sine of that gives us 25, should round to 0.251. Not going to make a difference in my plotting. Oh, that's a second mistake. 0.34, arctan, 0.534, and the sine of that, 471, okay. Second mistake over here with the last digit for rounding. Might check them all now. I've just spotted my mistake. The original one was right. Oh, what a fool. I was typing 335 instead of 355. Everyone does it. So let's try and get these uncertainties again properly for that one, because that is actually correct, 0.355. So let's do the sine of the arctan of, and let's get the biggest possible number we can. So it's let's chuck some more brackets in. I don't know how brackets work on this horrible calculator. 0.355, add 0.004, and then that's divided by, and it's not 1, it's going to be the smallest number possible, which is going to be the 1 subtract the 0.01. 34, exactly 34.0. So the top error bar should be 34.0 up there, which is where I'd originally drawn it. Annoyed with myself now. Now we're going to do it the other way around, so add and subtract, using the editing feature on the calculator, which doing my best with it. So 32.8 would put us about there-ish, which is roughly where it was before. So actually, the original data point was right and it was just outside. And now I've scribbled it out, I can't draw on it properly. Fool. But the line is right, and I had actually got that right the first time round. 0.338 or whatever it was. Oh, let's do it again. And get rid of the uncertainty bits. 335.335. It was what it was originally. So that was actually plotted correctly. Doesn't matter, I've got my lines now. So now what I'm going to do is calculate the gradient of these lines, and that will be the wavelength of each. Don't have a lot of room to do that, so let's just try and cram it all up in here. The red one, the wavelength is going to be equal to the gradient, and I'm going to pick 2 points along this line. I'm going to pick that point, because that's quite close to some grid lines, and what else is quite good? There is really good, very close to some grid lines. So I'm going to use those 2 points, just like that. I've written down the coordinates of them. This one is at 1,160 times 10 to the 3 on the x-axis and 0.75 on the y-axis. This one is 380 times 10 to the 3 on the x-axis, 0.25 on the y-axis. Usual gradient calculation, difference in y divided by difference in x. So I've written that down, and even though I can do 0.75 minus 0.25 in my head, I've written it so that I can see clearly where the numbers have come from. That's the gradient calculation, and I've got 641 nanometers for the red. It's supposed to be 650, and I can do some sort of error analysis on that later, so maybe I'll leave a little bit of space for that. And let's just do the green one here next. Green. I'm going to pick 2 points. One on a nice grid line, makes it easy to read the numbers. I'm running out of room here. Let's go down here instead, see if there's any good points down here. Oh, there aren't any really easy points. That one's not bad, so I'll use that one. And something, it's got to be at least sort of 8 centimetres by 8 centimetres away. So we're looking over here somewhere, probably there. Just check that that is sufficiently far away. Yeah, that data point is sufficiently far away. The further away these points are, the better. But that's a nice one, so let's go with that. That's 950 times 10 to the 3. 950 times 10 to the 3, 0.5. Oh, I always write the coordinates on. This one over here, I'm going to struggle to get the coordinates to fit in here, but I'll do what I can. Right there is 410 times 10 to the 3, and that is 0.225 when reading off the y-axis. It's exactly between 0.20 and 0.25, 0.225. So the gradient calculation, I'm going to put subscript R, subscript G, just in case I want to use those later. Write in the same numbers, do the same calculation. And so with that one, I get 509 nanometers. 5.09 times 10 to the negative 7, 509 nanometers. Yeah, not terrible. Again, it should be 532. I reckon, at least that's even what the laser says, and that's what the website said it ought to be. So a little bit lower, that's a bit lower, that's a bit lower. It sounded like some sort of systematic error. And we can think about what that might be in a second. Something that doesn't change the gradient, does change the gradient, so likely to be some issue with X, I suppose. Right, now let's do the same one for the violet. Violet, pick 2 points. That one looks quite nice. All the way down here. Really nice one. That's probably about as good as we're going to get. Then we can write the coordinates down. So this one here is 1120. What was that? No, it's not the same as that. 1120 times 10 to the 3, and that is 45, 40, 40, 41, 42, 43 and a half, 0.435. That's that coordinate. This one down here is 420 times 10 to the 3, and that is 0.195 in the y-axis. Type in or write in our gradient calculation. 0.435 subtract 0.195 divided by 1120 subtract 420 times 10 to the 3. It's always very amazing when you do these calculations and it just kind of works. So 0.435 subtract 0.195 divided by 1120 subtract 420, all those to the power times 10 to the power of 3, and give me a decimal. There we are, 343 nanometers. That's really too low. Wow, 343 nanometers. That is quite invisible. Check I haven't been a numpty with my numbers. No, I don't think so. 400, 1. No, I haven't been a numpty with my numbers, but that is not visible radiation. And yet, there I am with my violet saying it is well outside. So I'll have to think about uncertainties with this. But let's move on to the next one first. And if we have time to worry about uncertainties later, we can. Because it's not required for A-level. And we've kind of thought about uncertainties with the error bars to choose the gradient. Choosing another gradient, what we would do, I'll tell you now, we'd choose another line that's kind of acceptable, but it's not the best line of best fit. We'd take the gradient of that, or measure, I should say, the gradient of that. The difference between them is the uncertainty and the gradient. And we could use the uncertainty in the gradient as the percentage uncertainty of the gradient is the percentage uncertainty in the wavelength, because the gradient is the wavelength. I'm really tempted to do that now. Let's just do that now. Right, let's pick another line. Oh, I've just spotted something. While I was choosing another line, I've realized a bonehead mistake. If you were in the comments frantically typing before, you've done this wrong. Maybe this is what you were talking about. Look, that's the violet point, not that one. I've drawn a line that goes through that, that, and that. And so the gradient is far too shallow. It should be going through that, that, and that. What a numpty. Let's just cross that out and try another one. You should always use a pencil, ladies and gentlemen. All right, let's try that again. Line of best fits. Where am I going to get this? Probably about there-ish is as good as we're going to get. That is definitely steeper. Let's pick some points on the line. Kicking myself, but there we are. So many mistakes in one video. 320 times 10 to the 3 and 15, 14, 13, 0.13. That's the coordinate of that. Let's cross out that violet there. And let's use a data point up here. That one looks good. So that is 150 times 10 to the 3 and 0.455. Right, those data points. So violet wavelength of V is equal to 0.455 subtract 0.13 divided by 1150 times 10 to the 3 subtract 320 times 10 to the 3. Why I've written it like that, I don't know. Calculator. Here we go. So 0.455 subtract 0.13 divided by 1150 times 10 to the 3 subtract 320 times 10 to the 3. Oh, that's healthier. It's still low, but 392 times nanometers is a much healthier number. Still a bit low, but much healthier number. All right, now, what we can see here is A, the importance of using a damn pencil, but B, something very important. It's easy to make mistakes. Everyone does it, and that's okay, because as I said, this is a lab book. It's a working document. You're going to make mistakes, so that's okay. Let's pretend I did it deliberately. I can compare what I expected to what I got. That's why it's so important to have references and actually do that sort of looking up. And I like to do it first. What am I expecting to get? So I know what I'm aiming for. These are all a little bit low. And given that they're all a bit low, that is suggestive of a systematic error somewhere, which changes the gradient. And I don't know what that might be. I mean, it could be one of these, for example. It's actually less. If it would be less, that would mean the data point would be further back, which would be a steeper gradient. So maybe this is actually less than 1,200 lines per millimeter, but I can't tell that because I can't easily measure that. So it could be something like that. I mean, there's manufacturing tolerances, and I don't know what this actually is. So let's move on to the second practical we did, which was Young's slits. Again, we're going to try and determine the wavelength of those 3 different laser diodes. This time we're going to plot W on the y-axis, there they are, and on the x-axis we're going to plot D divided by S. Well, S is the same each time. D divided by S is that, times 10 to the 3 all the way down. This is, I suppose, very important. We're going to be dividing something that's times 10 to the 3. This is on the y-axis, so the gradient's going to be changing that divided by the change in that. Change in that is going to be having times 10 to the negative 3 in it. Divided by something times 10 to the 3 is going to give me something times 10 to the negative 6. Probably the right order of magnitude, looking at some of the numbers. So, actually, I'm not going to worry about the power. I'll deal with that later. So what's the smallest number? 200, let's call it 2.4. And the largest one, let's call it 6.6. 2.4 to 6.6 in the y-axis. So what I'm going to do is go 2 millimeters here. And I'm going to go 2, 3, 4, 5, 6, 7. The data will occupy about that much space, which is more than half of the available paper. But it's enough. Right, now let's think about the x-axis. So the x-axis goes, it's the same each time, from 6 to 10. So what we do, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10 works. It's nice and easy. That'll make it quite easy to plot as well. Straight line. Still using a pen, should be using a pencil. And so that's going to be, this is all times 10 to the 3. I'll include that in the quantity up there. So 6, 7, 8, 9, 10. 6, 7, 8, 9, 10. Trying to make sure my decimal points along here is consistent with that. Same as I did there. That scale should be consistent with that as much as I can. Now in terms of labels, I'm going to label this as D, S to the minus 1, and then think about the units. Well, D I'd measured in meters, and S I'd converted to meters when I calculated these. So actually there aren't any units for this. So it's just, all of those are just divided by 10 to the 3. Units are up there for millimeters. Just going back a step, there's no units for the sine of an angle, it's just a ratio of lengths. But on the x-axis here, that should have had a unit. So I should have labelled this x-axis something like n, d to the minus 1, and then thought, what's the unit going to be? Well, that's going to be in, d was the distance between in meters, and this is the reciprocal, so it's going to be meters to the minus 1. Just like that. And then you look back at the table and you go, I've messed up that unit, because that is the reciprocal of D, which means that should be in units of meters to the -1 as well. That's why it's important to check these things. That would have cost me my competency 4 in my A-level. Making all sorts of mistakes in this practical, but we're picking them up and fixing them as we go along. I actually think it's quite useful to watch that process in action. Maybe you get bored with it, but I'm hoping you find that useful. Right, let's get these points plotted for red, green and violet. And there we go, that's the points plotted. And you can see they form what looks close to a straight line. It's perhaps a little bit curved. Yeah, you can see there's definitely some curvature there. They get closer to the line in the middle and further from the line at the edges. There is some curvature there, but I think it's pretty close to a straight line. Do a quick uncertainty check, see if we can draw some error bars, which we possibly can. So again, I'm just going to look at the two extremes and see what they look like, because we haven't taken repeats or anything, so it ought to be fairly consistent error bars. It's not like we've got random error, which is increasing a spread of results, increasing size of some error bars and decreasing it for others. It shouldn't be like that for this. So if the error bars are roughly the same for both, I can just use the same error bars. And if they're not, I'll just use the larger one, because it's just an estimate. So what's the percentage uncertainty in NW? Because that will be the same as the percentage uncertainty in W, which I can use to calculate the absolute uncertainty in W. So let's just take this one here, which will be the larger one. 0.2 divided by 31.2. So that is less than 1% uncertainty right there. Then I can multiply it by that, so 3.9 times... and that gives me 0.025 uncertainty in W that I've plotted. What data point was that? That was this one down here. Well, each of these small squares is 0.05 on the y-axis. 0.05. And the uncertainty of this one is half of that. So I can't draw vertical error bars. Let's just test the other end. So 0.2 divided by 52.7 gives me very, very small indeed. Multiply that by 6.59. That gives me less than 0.05. It's actually about the same size error bars, which is half a small square. So I can't draw vertical error bars. And that's going to be the same for all of these. What about horizontal error bars? Well, let's check it. We have no idea what the uncertainty in S is. Probably could look it up, could do some research and then reference it. I'm not going to do that. Already done some looking up, and time is... It's an A-level practical. It's not a big deal. It's just an A-level practical. At university, you go into more detail, you take more care. We're using the same uncertainty in D, aren't we? So what's the uncertainty in D? 1 centimetre. So let's go with the largest one. Yeah, let's go with the largest one. So 0.01 divided by 1. Why am I typing that into a calculator? That's the relative uncertainty of that. And I'm after D over S, and I don't have an uncertainty in that, so I guess it's just that. Times by that value, which is 10, times 10 to the 3, which is handled in that, gives me... So 0.01 times 10. Again, why am I typing that calculator? It's 0.1. If I look here, can I make that fit? So 6.5. Oh, yes, I can. It's 2 small squares. Let's just check the other side. Down here. So 0.01 divided by 0.6. And then multiplied by 6. I hate these calculators. Is 0.1, which is 2 small squares. So it's 2 small squares. Great, I've got error bars. They're horizontal error bars, but I've still got error bars which are 2 small squares. Kind of wishing I hadn't done this right to the edge now, but there we go. 2 small squares. It's good to think about these every time you do any sort of practical it makes the best fit line easier to draw. There's a larger target to hit. And you can make better judgments about how your best fit line should go. So I would absolutely recommend error bars every time. I mean, that range of results there is not huge, but bear in mind I'm plotting them all on the same set of axes. So we've got about 11 centimeters of space on the paper just for the red ones. Really, that's not very much. Let's look at that. Fantastic. If I do that and line that up, I can get that to go through all of the error bars. I think that would just go through there. And that's red done. And I can measure the gradient of that, and that will be the wavelength. Let's do the green. Let's get them plotted. Might as well plot the green and the violet now. You don't need to watch me plot things. So there's the points plotted with error bars. I mean, all of those look like they're almost in a perfect straight line, except for that point there. So let me just have a look at that point and make sure I've plotted it correctly. 5.26, 5.2, I have, yeah. Okay. It could either be an anomaly where the universe gives us slightly different data than what we expect, very interesting, unlikely, or it could actually be a mistake. But given that it's just 1 point and everything else is so perfectly on the line, I'm going to discard that point. Boom, it's discarded, I'm not using it. So this is green. Now I'm going to have to justify why I've discarded that. Do that in writing somewhere, don't need to do it now, but I've discarded it because it does not follow the pattern. Simple as that. I think that I made a mistake. Not an error, a mistake, which is why I'm discarding it. Gradient of that is only slightly lower than the gradient of the red. Okay, fingers crossed this all works. Let's do the violet one. There they are for the violet one. They look like they follow the trend pretty well at the top there, and that point down there. That one would be within that trend as well if the error bar went far enough left. That one is the awkward one now. So if I try and get all these to line up, let's just push it through there, through there, through there, through there. Pretty much as close as we can get. I think that's probably the best line we could get. And you can see it's almost there. Now, in truth, we probably don't have to discard this point. In truth, we don't have to because we haven't included the uncertainty in S. And I don't know what that uncertainty is. I mean, that could be as high as 0.15. Okay, so we go like this. That's an extra 50% uncertainty. I don't know why I typed that in the calculator. Extra 50% uncertainty, which would push these error bars way out. And it'd be really easy to draw straight lines that pass through each point then, but I don't think that's sensible to make that assumption, and I don't know what the uncertainty of that is. Right, let's label that violet. Let's calculate these wavelengths. So pick a point on the line. I'm a bit worried actually with the violet one, because the line itself doesn't extend over 8 centimeters. Which really is the smallest distance apart on a graph that you'd want your data points to be when you're doing a gradient calculation. The violet one, I'm not going to get a very accurate gradient. But hey-ho, we'll do what we can. Let's label these points. So this one here is 6.25. times 10 to the 3, I'm going to include that multiplier, that's going to be useful for me when I do the calculation so I don't forget it, 4.10. And then this point up here is, let's come down here, 10, 9.9, 9.85. 9.85 times 10 to the 3, and 6.55 on the vertical axis. Okay, let's write up here red. The wavelength of the red is going to be the gradient. So that's going to be the difference in the y-axis. So that's 6.55 subtract 4.10, divided by the difference in the, let's try and make this straight for you, divided by the difference in the x-axis, so that's 9.85 subtract 6.25, all to the power of, all times 10 to the power of 3. The calculator out. 6.55 minus 4.1 divided by 9.85 minus 6.25. 600 and, hang on, there's a power of 10 wrong somewhere. Oh, it's millimeters. What a fool. Times 10 to the negative 3. They're millimeters. All right, so that is 681 nanometers. Compare it to the other one. Well, that's too high, that's too low, compared to what I think it should be. Somewhere between those two, that's reassuring. Let's do the same thing for the green. Lambda G. And you don't need to see me do this every time, so let's pause the video while I do it. All right, so that's the calculation done. I picked points as far apart as I possibly could, because I wanted it to be as accurate a gradient as possible. Chucked them in, remember in the 10 to the negative 3 this time, got 568 nanometers. Again, 568 is a bit bigger than that, 509 is a bit smaller than that. So that's, again, it's reassuring. It's a shame they're all a bit higher. It'd be nice if they were actually right, but never mind. Let's go with the violet one. Let's make myself a little bit more room. Violet, so lambda V is equal to, and I'm going to have to pick points as far apart as I can here. Really far apart. It's not quite enough room vertically. It's 1, 2, 3, 4, 5, 6, nearly 7 centimeters vertically. It should be a minimum of 8, but it's the best we can do. It's just the way it is. Let's do the calculation. Okay, so I picked the points really far apart. I entered the numbers, put them into the calculation. Got 420 nanometers. Just like before, that is more than I expect, whereas in the previous experiment it was less than I expected. So, now I could write a conclusion. Well, I don't really have any room. I don't want to start a new page for a conclusion. But it is at this point that I could conclude what I found. I could do a worst line of best fit, and then here I could do the same sort of thing, and then find the uncertainties in these. But it's such a big practical anyway, and we've done enough that I think there's enough there for competency 1, if I was given written instructions to follow. Competency 2, I've systematically thought about what I was doing, discussed how I was keeping the control variables the same, how I was influencing my will over the independent variables, how I was making measurements, what instruments I was using and why, especially with the vernier calipers. Had a little think about error analysis. Competency 3, I talked about the safety involved with using a laser and not putting the shiny vernier calipers in the laser beams to preserve my vision so I didn't get blinded. Competency 4, units. I've not got units there because there aren't any. Units. Everything looks correct. The units are all correct because I corrected that one. Units are correct there. I need just to cross that bit out. That doesn't have a unit because it's just a ratio of lengths. Units, it's all fine. What else have we got? Competency 5, the use of the graph, calculations, referencing what I should have got, and comparing that to the results that I actually obtained, which I've done verbally, and I could just write that as a very simple statement there, but I don't want to take up more paper than is necessary. So 1, 2, 3, 4, bit messy, made some mistakes along the way, but that is this practical done.